getting a popularity. Then from the biodegradability point of view, from the environmental sustainability concern, people are mixing natural fibers into the matrix of polymers particularly to make a composite. Because they increases the modulus, like elastic modulus of the material, they increases their strength, density, and yes, they also balance the force of it. So, if you take the short fibers, that short fiber may be randomly orientated, and accordingly they will give the properties of that particular composite. On the other way, if they are continuous means they are greater than certain length. Then yes, if they are oriented in a particular direction, so they will enhance the properties accordingly. And third thing in the composite is about the fiber and reinforcement interface. That interface is critical because in those composites, failure is possible to occur at those points. Like if the binding of those fibers, you can say reinforcement, and your matrix is not in a good way, then it can pull out. So it will not take the load, or it will not transfer the load from one to another in the matrix. So debonding can occur. Similarly, the crack deflection is, if it is properly binded over there, then it can deflect the crack, otherwise not. So anisotropy in composite materials, yes, that's intentionally done. As in case of metals, the isotropy of the metals is popular, and that is desired also. But in case of composite, we require specific property as specific cross section. Like take the example of our teeth. The outer layer of the teeth is hard, while the inner part is comparatively soft to bear the load of chewing or crushing. While the outer layer has to be tough because it has to protect it from the wear and tear. So material is same while properties on the out part are different. Similarly, in industries like where you are producing two gears, they are meshing together, and you need a harder surface on the outer of the gear. Similarly, on the inside, material should be softer comparatively to bear the load or impact shocks. So, anisotropy comes from the reinforcement. Either that reinforcement may be particularly done on specific sections, that may be directional, as we have talked about the fiber orientation, or the density of reinforcement has been intentionally changed. Like in nuclear industries, in thermal power plants, the high temperature bearing property of inconel materials are favorable. But inconel is costly. That's why we make a combination of stainless steel and inconel. So on one side, where high temperature strength is not required, means outer side, we keep stainless steel, but gradually we change the composition inward as an inconel material. Similarly, in dual turbines, in jet engines, double engines, so one engine which is shorter comparatively has to bear the pressure on the lesser side is made up of the stainless steel, while on the other side it is made up of inconel. So yes, we intentionally do the anisotropy in these materials. So these are the aspects like the production. If you want, you can tailor for the composites. But in case of metals, there is a standard process of heat furnaces you have to produce from the ores. Properties is process dependent, depending on the process, laying down or mixing, you can change them. Strength to weight ratio for the composites is very good. The strength to weight ratio give the composites an upper edge as compared to metals. Similarly, other properties. The industries like the Reebok, Puma, they are producing the shoes according to the athlete foot shape, size, and requirement. And those materials are, yes, definitely they are composite materials. And they are producing it as per the need of the athlete, as per the shape and size of the feet of the athletes. And they are popular. Yes, nowadays that thing is comparatively costlier, but in certain time definitely available to all of us at a lower cost. So the polymer 3D printing, similarly, I was studying an article about the teeth crowns, the hearing aids. The companies are making $1 million through these small innovations, like the hearing aid. If we produce in a standard shape, like mass production for a standard shape, that available shape and size may not fit everyone because the hair anatomy is different for everyone. So some irritations, tightness, looseness, that factors are always there. So companies targeting that they are scanning this part and accordingly designing it and producing it from the composite materials. Composite why? Because they have to incorporate some sensing devices, some electronic devices, outer case. So they are material of composite. Similarly, the teeth crown I was talking about, like the aligners, teeth aligners. Suppose there is a person who have 30-degree misalignment of the teeth. So what they are doing is the 30-degree can't be done in a single go. They give it with crown for 5 to 6 weeks for 5-degree correction, and then they Fourier into the second set of again 5-degree correction. So 30 degrees divided into 6 segments, and you can fit them yourself or through the dentist. But they are producing it by scanning the jaw shape and size. So they are customizing it accordingly. So now come to the 3D printing of these composite materials. Yes, we are familiar that the additive manufacturing, which is also known as a 3D printing process, is classified into 7 categories. The ASTM F42, the committee responsible for designing the standards and regularizing those standards throughout the world, is this ASTM. And ISO and similarly our Bureau of Indian Standards all are taking reference from ASTM. So they have divided it into these 7 classes. Every process which is available for the additive or 3D printing is among these categories. So before this was done in 2015. Before this, everyone was giving a different name to this technique, and they are popularizing their names. Even the FDM, which is very popularly known among us, fused deposition molding, is a Stratasys name. It's a proprietary or trademark of that company. So they have divided into 7 classes. So if we talk about particularly FDM, so FDM comes under the material extrusion class, where material is extruded through the nozzle. So it is also known as a free form fabrication, triple F. Another is like for this side material jetting, where material is in liquid form and we have a control of each and every droplet. And specifically, we are dropping it as per the design requirement. That's the material jetting class. Similarly, VAT photopolarization. VAT photopolymerization is VPP. The example is stereolithography. Stereolithography comes under this VPP class. Binder jetting, the polyjet product of the HP and Stratasys, they comes under the binder jetting. Over here, this binder jetting is similar to the inkjet printing process. Nowadays we have laser jet printers, Before that, there were inkjet printers, and the printing principle of these printers is like they draw the ink as per the text which we want to print on a paper. So similar, according to this strategy, we have a powder on the platform, and the binding agent like glue, adhesive, is drawn as per the requirement where we want to bind the particles of that powder on the platform. So that's the binder jetting. Another is powder bed fusion. So powder bed fusion is different from binder jetting. The similar point is both have the loose powder particles on the bed. That's the one thing. But in PBF, we are fusing them together. Fusing means either we are doing the sintering or we are melting them. Means we are heat treating them. But in case of binder jelly, we are just dropping the binding agent on those particles to get binding. So in powder bed fusion, generally the laser power source is used. So if it is a metal, definitely we have to fuse it. But if it is your polymer, then we have generally we go for the sintering of that because of melting the property of the polymer get somehow changed. Another example is sheet lamination. We all know that the laminates like these, they are made by hand, the wood laminates and all that. But if this process is done through the automation with a design pathway, then it can be named as a 3D. Another is directed energy deposition, where the material is supplied directly in the energy source. The example is the application of welding known as WAN, wire arc additive manufacturing, because in case of welding also, we make use of a wire, and that wire is directly fed into the electrical arc, and it is melting and depositing on the plate. So the heat source can be changed to the electron beam, it can be changed to the laser beam, and similarly that material can be supplied to it, either in the wire form or in the powder form. Both kind of DED, both are DED technique, directed energy deposition. So these are the 7 classes of additive manufacturing processes. So for the composite materials, yes, all techniques are available, but particularly for polymer, if we talk about the material jetting, wet photopolymerization, binder jetting, and material extrusion. These are popularly utilized for polymer composites. In case of powder bed
हेलो
fusion, there is a technique called as SLS,
बढ़िया
selective laser sintering, which is used
हाँ
for the
नमस्ते जी
polymers particularly, polymer composites.
हाँ ठीक है
So
हाँ
when now the printing of these
बढ़ रही है
composites, particularly specifically again and again telling about polymer composites,
थोड़ी बहुत
the
5-7 हज़ार
biggest challenge is about the wear
थोड़ी बाद में
of
बात कर
your
लेंगे
nozzle.
कि नाम है कौन सी
From
ब्रांच
which
में भेज
material
दे
is
कितने का
coming
भेज दे
out. I think all of you
हाँ
must
पीछे
have
तो कर दी
seen
मैं
the
पीछे में
previous
मेरा
city of
ब्रांच
white college.
डिपार्टमेंट मेरा ही हुई है
They have a good
नो
machines
बताओ
for
मतलब किस में
3D printing.
वो क्या नाम है डिटेल भेजना उसकी
So
बात करके देखते
in
हैं
that FDM machine, a
हाँ
filament
अभी फिलहाल तो
of
अभी मीटिंग
polymer
है
is there, and
अब
that
भेज दो ना
filament gets
डिटेल भेज
collected,
दो
come out through the nozzle and get deposited. So if it is of ABS or PLA, that kind of material is there, then the brass nozzle is used, and it is well, you can say sufficient for this purpose. But in case if we are mixing the reinforcement like carbon fiber or graphene or glass fiber, then brass is going to fail. Its dimension will deteriorate or even it can glow during the printing. For that purpose particularly, we need hardened steel nozzles or at least the stainless steel nozzles for that. The standard dimensions for those nozzles can be as per the requirement. The standard is 0.4 mm, and similarly you can go with 0.6, 0.8, 1 mm, and 1.2 mm. But that depends upon your requirement, because accordingly you have to design the chamber which is collecting the filament and melting it. Similarly, the flow rate you have to maintain. The diameter of the filament which is feeding through the rollers, yes, again, you have to take care of the rolling mechanism that it can sufficiently fill that cavity. So when we add the reinforcement, then these two concepts can be, you can say, interplay in this 3D printing. This is in-nozzle and co-extrusion. So in-nozzle means your matrix and reinforcement, they comes together from a single nozzle. You are mixing them in a single chamber and they get produced, melted and deposited. While for co-extrusion means you have two different nozzles and from one nozzle your matrix material is coming and from the another nozzle your reinforced material is coming. And then you are laying them on the surface or substrate. So two kind of concepts or machines for printing of polymer composites are used. So if we talk about the materials for the matrix particularly, then clearly ABS battery, similarly polyamide, polycarbonate, TPU, these materials are highly used. But we have divided them into two categories. One is commodity material which are easily available like ABS PLA, they are available at 700 or 800 rupees per kg, the filament. While when we require the higher strength or you can say as a functional component, because the life of PLA, ABS, packaging components is very less. PLA component, its dimension will get deteriorated after 4 months, and you can say it will be out of use after 6 months. Because glass transition temperature of your PLA is very less. It is 60 degrees Celsius. So on the rise of the temperature of the working environment or something, it also absorbs the humidity and moisture from the atmosphere. So it deteriorates properties and accordingly functions. But PLA is very print friendly. Anyone, if he or she wants to try the 3D printing, then PLA should be the first choice. Because it is very print friendly, it's not temperature sensitive, you can print it by opening the door or top of the machine. While in case of ABS, if you want to print it, then it is yes, difficult to print. You have to close the chamber. You have to maintain the temperature because these materials are temperature sensitive. They will wrap, they will curl or deform. These engineering thermoplastic materials are costlier. So if we require a functional component in the machine which should bear the load of that application, or it has to be corrosion resistance or some particular fatigue properties, then these engineering grades are used. Adhere to the substrate or the subsequent layer which is already deposited. So how it make a bond with it is again a criteria. The thermal stability, yes, the sensitivity and all that, how much stable it is or chemically degrading or something. So yes, thermoplastics can be recycled or reused, but for how many cycles? Like it is suggested that if you want to reuse a already printed material by crushing or mixing it, so in any case it should not go beyond 40% of the total. Means at least 60% virgin material of polymer should be there in case of you are producing a filament which is carrying some reusable parts. And if you talk about the number of cycles, that how many times we can reuse it. Like suppose we have printed a component and we have done our job. Now we want to crush it and want to mix it again to produce a new filament. Then that number of cycles you can do is suggested is around 3. Beyond that, you can do it just for a sample fit form. Its properties will be very, very low. So, similar The scenario with the reinforcement, like short fiber or continuous or long fibers. So, which reinforcement and similarly, how much long or how much continuously you can feed the reinforcement. So, again, there is a criteria or you can say trade-off between the printability and performance. So definitely it will enhance your performance if you can provide a continuous reinforcement because it will give you an orientation, defined orientation. But definitely its printing is not going to be easy. Either you have to make use of a dual extruder or some other arrangement. Because control of reinforcement orientation is tough. So in 3D printings, the process parameters, the structure which we are producing in terms of density, in terms of orientation, defines the property in that printed component. So if we talk about the parameters like your nozzle temperature, your bed temperature, so bed temperature is very serious things to be taken care of. Like if your bed is at the room temperature and you are printing with any material, then definitely it is not going to adhere on the platform. Another thing, if anyhow you have managed that adhering, then definitely it is going to curl or wrap from the sides. That happens because these materials have a glass transition temperature. As we have talked about, the glass transition, as the name suggests, the materials behave like a viscous material. It loses its properties, its mechanical strength and all that. So like PLA loses its strength at 60 degree. ABS loses its that strength at 90 degree. So accordingly, the nylon, polyamide, their glass transition temperature are on higher side. That's why we can make use of those metals at high temperature also for thermal stability. The print speed, your layer height, is it going to be bind or not? The infill pattern, I will show you in coming meetings what is infill pattern, and the density. You can produce a 100% dense component or you can print a 70% whole, means only 30% material of the total design is there. So that depends upon your requirement and accordingly the property will be affected. The raster angle, the lines which are deposited are called raster infinite lines. So their angle may be 0 with the horizontal, that may be 90, or that generally kept as 45 and reverse with 90 degree, that plus 45 and minus 40. The number of perimeter or shells, the outer perimeter. So in 3D printing, we have a freedom that we can define it. We can keep it 2 or 3 or as per our requirement. So outer shell perimeters give us the strength to the component. The void and lack of fusion between the rows, definitely that is going to be the issue. Because it's a continuous deposition. And while your material is, your nozzle is taking a turn from somewhere, then definitely on that turning point, the material deposition will be either high or low. Because at the same time, it has to deaccelerate towards that point and immediately it has to accelerate. So that control in that machine system is a major part. So interior bonding, yes, we have talked about that polymer composites or any kind of composite have an anisotropic behavior. Yes, that anisotropy is intentionally designed, you can see. We want that because the requirement of our composite is such. But along with the anisotropy of producing the composite, anisotropy due to 3D printing of composite also comes into play. This anisotropy is the z direction which shows the poor mechanical properties in the material. So in z direction, your material shows the weakest properties. Because suppose we are producing a part and it has, for example, it single poor layer defines the strength of the whole component. So it is going to fail over. So in XY direction, as alignment are there, threads are there, load will be taken care by those number of will be distributed around that. So its strength will be high in X and Y direction. While in case of Z direction, the load will be taken care by only the two layer bonding part. If somehow there is a defect or poorness, then your part is going to fail from that. Similarly, the fiber orientation is the fibers are oriented in a particular direction. The good properties or desired properties according to that. That fiber may be as per the requirement, they may be of metals for the thermal conductivity purposes. If you want to produce a polymer composite with thermal functions, that may be some magnetic behavior can show. They can give you electrical conductivity. So that's totally upon you that how you are going to select the materials for your application. Yes, please. Overcome this. Is defining the standards for these. So it is defining the standards for these. So they are defining it as the requirement is coming. Or yes, they are also considering the future, but yes, the case is less. So every year a new technology of additive manufacturing is produced by the companies. They are claiming they have to justify either it's a mix or different. So accordingly, these standards are being defined. So yes, currently, if you search those years, any standards, BIS standards, European standards, there are I think 3 or 4 standards about 3D printing. So still they are demanding the academicians that we can collaborate with the I also sir, I also sir, that they can sign an MOU with BIS and they select few professors from your institute and they are assigning the projects and giving this responsibility to produce the standards for different things. And difficulty achieving high fiber volume, we can't go like 80% fiber and 20% matrix. So it is not printable. It will not come out through the nozzle. So there is a limitation of the mixing of, if I talk about the practical point of view, around 15% reinforcement is mixed with the matrix, which is easily printable. Beyond that, there are nozzle clogging and all those chances are very high. So from the sustainability and life cycle considerations, yes, we should take care of those. So you should print responsibly and by looking at the environment. As we have discussed, that PLA is print friendly and at the same time it is biodegradable. And people are going toward the natural fiber mixing in PLA. So when you will search the literature, you will find a lot of papers nowadays coming out from PLA with carbon fiber, sorry, PLA with wood fibers, jute fibers, and all that. So bio-based reinforcement and matrices are. So next thing is where our future for this polymer composite or for particular composite 3D printing is going toward. So one is about the multi-material. Now, as the science is rising fundamentally as well as on the technological part also, so we need new materials for the new innovations. And a single material can't fulfill the requirements. So definitely we need a single component but made up of multi-materials. So in a cross-section as we have discussed about the tip, about the gear and all those, you need a single component with different materials or the single material but with different density at the cross-sections. So functionally graded metals are the future from that point of view. Another is about the in situ monitoring or closed loop printing of the process. The machines which are available in most of the labs in academic institutes is an open loop control machine. Yes, you can sense that it has printed the whole component, it has executed the command, but there is no closed loop control that it can't take the feedback and give to the controller for the automatic resetting of the parameters. Suppose if defect is occurring in the printing, your machine uh, has no vision to see or no provision to automatically stop it because it has no sensors from that point of view, no feedback signal to the controller that either it can take corrective action or shut down the process. So that's the another window where we academicians can contribute by designing some in situ monitoring of the process. Another is about the topology optimization for the performance of your component. That this quantity is same, but we can redesign it. In our institute, there was a visit from the Air Force Wing, and they told us that in some helicopter, one component, the helicopter was imported from other country. So now they are not supplying the spare part. And gear component of that helicopter has damaged. They want to produce it and even they don't know about the material of that gear because that country or that industry is not disclosing that because they have their patents and all that. And in India, in case of materials, we are mostly dependent upon Russia in case of metals. And another is Israel. So they need the material selection for that, and accordingly they want to make the same component because they don't know the material. Similarly, they don't know about the manufacturing process which can produce that component in that certain characteristics. So they want to try it with 3D printing, and when they designed it with 3D printing, just only for the design purposes, now the material was less as compared to the previous one. That happened because when you print through casting and do some machining later on for the finishing and all that purposes, then you need some extra material to hold it. And similarly, extra material for bearing the forces of machining because tool is going to make a direct contact between with your workpiece. So holding pressure as well as pressure of cutting of the tool it has to be there. So they design it with extra allowances, extra material. But in case of 3D printing, there is no holding pressure it has to be. Similarly, there is no extra passage for the tool, possibility of tool coming or accessibility of the tool. So you can optimize the design of the parts also in 3D printing. And next term is 4D printing. Now, as per the requirement and the applications, the things are moving from 3D to 4D. So 4D, from a paper I wrote this for you. Like in 4D printing, this process is similar to 3D printing, but we have a stimuli. Fourth factor is your stimuli. That stimuli may be an energy source, a temperature, or your time factor. So like this was the material, liquid crystal. So material was liquid crystal elastomer. Elastomers are like which have a high elasticity, like your rubber band and those materials which can be this. So they printed this leaf part. They exposed it under a certain wavelength of ultraviolet rays, 450 nanometer. So its shape got changed like this. And at the room temperature, the shape was low to this. It remained like this. But again, they exposed it to a 65 degrees Celsius temperature for 5 minutes. It again recovered. So you must have heard about the shape memory alloys, the smart materials. So now the 3D printing of those materials is somehow related to the 4D. In biomedical also, this thing is required. So this was just an example of a leaf which is going to curve and open again. So they can be used as an actuator in your devices. So from this future, I have selected multi-material or you can say functionally graded material to give few glimpses of that. How we can design a functionally graded material. So before that, let's define functionally graded materials. Why we call it like this? Functionally graded means its function is graded, means changing from one perception to another perception. So that can only happen if in the matrix and reinforcement you either have a density difference, the size difference, the shape and dimension difference, the orientation difference. That difference may be continuous, like in the E part, or that may be step, layer wise. So accordingly, its property will be different. In the G part, you can see this is a simple composite where one side is metal and another side is ceramic, and they have a defined interface because the composition is totally changing at one cross section. So behavior or properties of the material will also abruptly change at that interface. You can see. So when we design it as a functionally graded materials, so we get a smooth transition of properties, either yes, that may be rise or lower, that depends upon which you want. But that transition is smooth, not abrupt. Because in such cases, in ordinary composites, there are pretty much chances of failure at this interface. That interface will have a very poor properties. So in FGA, the properties will be good. Similarly, the relation of position and property you can understand. If we have a abrupt changes in the compositions, yes, it is layer-wise. Suppose in C diagram, the composition is changes in 10% at each layer. Suppose. So properties are also affected in this manner as the A part of the figure. But if the transition is smooth like G, H, and F, then this property transition will be smooth. So that's the beauty of FGM functionally graded materials, and they are now getting the popularity in even aerospace and biomedical applications. So this is one case study where we have this stainless steel and inconel material. So from one side you can see 100% stainless steel, and on the other side 100% inconel. Inconel is a nickel superalloy which is used for the turbine blades, guide blades of your turbine engines, turbo. So you can see the properties of that material, how they are changing in that way. So this was the first part of my presentation. So next part is about the key characteristics and challenges while printing the polymer composites. So let's discuss that. just for the revising purposes, we have divided into seven categories. All additive manufacturing processes in seven classes. So we are particularly dealing with material extrusion for polymer performance. So yes, it's an extrusion-based process. We know that we rely on a standard STL file. This technique was patented in 1984 and first machine came out in 1987. And they gave a format for it that was the other process name was stereolithography. That's why they defined the both STL format for these files. So we make a CAD model and that CAD model is converted into STL file and that STL file is feeded to this passing software. So we all know that long filament is there. The work hand which carries the nozzle moves in XY and after that we may move it equivalent to the layer height of the part. And then extruded is solidified and poured welded to the substrate or the subsequent layer. So in that way, your part is printed from the base up. So if we divide the FDM operation, then yes, I think 7 steps are there. CAD file, then you slice a software, then you either make it a small size or a large it to fit in the work volume because your machines have a certain work volume defined work volume. Then orientation and positioning are very important either to optimize the parts on your printing platform. You want to 5 parts printing together, then you have to optimize the spacing. That's one thing. Another is about the orientation. Either you require some properties according to your requirement, so orientation have to be selected. Suppose there are two things like this printer casing I want to print. So one way is I can print it like this while standing on the platform, and another way is this lying on the bed like a horizontal. So now in which direction, which property will be good, or how much time is going to take, particularly in both orientations. So if I ask that in which orientation it will take more time to print, while keeping this as a horizontal like this, or making its axis and standing as vertical. So when I keep it vertical, the number of layers are increasing. So definitely it is going to take more time. In case of horizontal one, XY travel length is increasing, but the number of layers are very few. So it is going to take less time. That's the production rate you can say it with the production time. But another thing is about the requirement of property. In which direction you require the good properties. Like if you require the tensile strength in your material along the length of this axis. So if we are keeping it horizontal, then all threads will be laid down in XY direction. So all load will be bear by all these threads. So its strength will be put in XY direction. But in this case, if the strength between two layers, anyhow, out of 500 layers, if strength of between two layers is weak as compared to rest, your component is going to fail from that. So that depends upon the orientation. Similarly, there are few dimensions which are less inside its pointer. There may be some extrusions to hold the cells and all that point. So their thickness is very less. So they need some supports while printing. They can't be printed with support. So in that way, definitely orientation is going to be. Path planning, yes, path planning is again important. Path planning is done similar to the G code and M code of your CNC machines and any kind of machine. So that path planning should be such that your time is going to decrease and your strength has to be maximized. So path planning may be continuous, discontinuous. There are many methodologies given by the researchers. If I talk about the main components of it, the extrusion head, dry blow, the heating chamber, your frozen and your substrate. The slicer softwares nowadays, every company is providing it, and it is also freely available, open source, because it gives the popularity to that machine. So you can try any, but simplified 3D having a peculiar feature that it animates the process. It can show you as a video of the printing. So that's freely available. You can try. This technique is patented with them. That's why rest of them shows the image only, but this gives the video of it. So, in the initial part, I have discussed that polymer composites, they can be divided into two classes. One is commodity material and another is industrial grade materials. So definitely cost and performance are the two factors to decide. Like you can see, these commodity materials, ABS, PLA, PP, polypropylene, these materials are commodity materials. They are cheaper. And over there you can see the printing temperature of performance of lead post. Their performance is lower side, their post is on lower side. Printing temperature is also lower side. As you go up toward the engineering, polyamide like nylon, polycarbonate, TPU, PETG, they are industrial grade materials. PETG is a material for food grade material. Still, you need a high performance that peak and PI metals are there. It gives you a good metal-like strength. Not equivalent to metal, but near to that. But their post as well as their printing is not easy. You need some tricks with that and some sophisticated machines also for it. So this PPT I just kept for the reference purposes. If anyone wants to compare a material with its characteristics. So three materials generally in academia are PLA, ABS and nylon. So this is a comparison between the strength, stiffness and durability. So PLA have a good strength. It's print friendly. It is called print friendly. Stiffness, but durability is very less. Chemical resistance is less, and it doesn't show any heat resistance. As I told you that its glass constant temperature is 60 degrees, so it can't be a beyond that. While ABS, you can say strength is lesser than PLA, but durability and heat resistance are comparatively good. Next is nylon. Nylon is poor on strength part, tricky to print, but on the same side, durability and chemical resistance on the high side. So, according to your requirement, what kind of property you need in the print part for a machine, for a functional things, then you have to go to design. And the print parameters you have to take care of. Because if you want to go with a good combination of properties, definitely the print window of temperature is good. Printability means you are printing while producing minimum difference. Means it's print friendly, you can say. No, like it is coming continuously about one thing about the resource kind of thing. Another thing is about where adhesion between the layers. It is print properly about. Third thing is about the curling and wrapping of its components. Good printability means less temperature sensitive. If anyhow, suppose I am producing this part which has a in this orientation, vertical orientation, so number of layers will definitely have. So the bottom layer which was printed 15 minutes earlier, and now I am at the top. So the temperature of bottom part is very less, while the high side is around 200 degrees Celsius. So this this temperature variation can give kind of, you can say, thermal stresses, and definitely current trapping will occur at the bottom. So bottom either we heat the substrate or come like this. So I will show you some components. So we have to deal with those things. So in the third part we will discuss those issues and their remedies. So key features in a material extrusion like FDM processes is loading of material, its liquefaction in the chamber, the pressure, necessary pressure to come out the material from the nose. Like if feeding through the roller is continuous without any interruption, then definitely the coming of the filament in the heating chamber will give a pressure to the liquid material collected in the chamber and it will come out through the openings. So if it is just coming out due to gravity, then it will not come out properly with complete filling of the opening. But if some little pressure is created and only one way is there that we can apply the pressure to the coming filament, one thing. Then finally your extrusion has been carried out and as per the defined geometry you have laid it down. Or at this point we have again a thing like your orifice of the nozzle have 0.4 mm diameter, while you needed the layer thickness as 0.2 mm. So how that will be achieved? Because nozzle is running fully with 1400 micron, you can see the diameter of the coming out material is 1400 micron, but you require thickness of the layer as 100 micron or 200 micron. Then the bottom part of your nozzle has to do a flattening function also. It is depositing at the same time it is pressing it against it. Otherwise, we will discuss that point later on. Like, take the one scenario that the nozzle diameter is 0.4 mm and layer thickness is also 0.4 mm. Can we achieve that? Or if it is possible, because machine can execute as per the command, but the part will be in a good shape, size, or strength. So for the adherence of two layers, we need a little pressing. Little pressing is required for the bonding of two layers. So for that purpose, if the diameter of the coming thread is kept same as the height, then definitely it is going to make only point contact and the property will be good. So in any case, your layer thickness should not go more than the 80%. 20% flattening, at least 20% should be. So we will discuss those things. That can be adjusted by the selective printing speed. You have to carry out the lower printing speed, that more material is printed at a certain efficiency. So we will discuss those things in the coming weeks. And the very important thing is about the support structure which we provide here. The support structure is necessary because the overhanging component, the overhanging part, either the component will be broken like this, or some part of the structure will be overhang. Like these, when these roofs were laid down, so they have provided some support for the roof. So similarly, we can't print the material in air. We need some substrate over there to print that. So we need to provide some support for that. So we will discuss that. So print parameters which are important is your build speed, your extrusion speed, your nozzle temperature. The consistency will be decided by these parameters. Your nozzle diameter and your layer height they have a relation as we talked about, and your build chamber size. So as per the money spent for purchasing the machine, the work volume will be different. So in industries, 1 meter by 1 meter by 1 meter work volume can be obtained at a large size, like a chair size component can be produced from those machines. While in our labs, academia labs, generally for the small research or demonstration purposes, machines have a 200 dimensions. So issue of wrapping, which we were discussing now, that occurs because of the differential cooling. Can we show you this? Like this is the component which you have designed, and you have designed it like to be painted as a flat part. But after printing, the printing was going smoothly, but when it goes toward the finishing process, this kind of wrapping has occurred. And you can see the dimensions of the components. The wrapping of the edges. So definitely this occurs because there is a temperature difference between two parts of this. Like if I know about, I'm going to print this, and my nozzle has started from here, and the length of the part is so high that when I reach over this dimension, it has to be closed. Suppose printing this, and now again we print from that side only because of the continuity. So it will take more time for the next layer to be deposited over this section. Similar will happen. So this wrapping is an issue. Polymer composites, while printing media. So इसका solution क्या है? How we can resolve this issue? Any idea? How we can tackle it? So to tackle the issue, we change the orientation of the part. We do not print it like this or we do not print like this. We print it at certain angle. So 20, 10 to 30 degree orientation angle is given. That is heated at up to the glass tension. So it is 60 degrees. So if I talk about the heat, it's 60. If it is 80, it's 69. But the layer which is pointing on the top, like, its coming out temperature is 230 degrees Celsius. So it is 210 around here. So still difference is more. And dimensions are less to you can say conduct the heat. They are accumulating it high because the thermal conductivity of polymers is poor. So that's why this kind of thing. So to tackle this issue, we print the part at certain orientation. So definitely we have to provide the support structure in case of orientation change. But yes, at each layer the length of the part is changing. So we are removing the chances. So layer adhesion, again one diagram I want to show you. That this is the point which I was discussing with you. That this is the nozzle dia and the same dimension extruded is coming out. So if similar dimensions are laid down like this, then this adhesion will be just a 0.9. So the adjacent part to the orifice, like this, have to be there in the nozzle. So you will see in the design of the nozzle that along the orifice on the both sides, some part of the nozzle is flat, and that is flat just to give a pressing action. So that pressing action confirms the adhering between fluids. So you can see this height get compressed. So it suggested that at least 20% compression should be. Means height, max height should go beyond the means height should not go beyond the thickness of your orifice. So a 0.8 times of the orifice it can be max. अगर 20% आपने प्रेस नहीं किया तो जो कंडक्शन है so like this you can see the some part of it alongside the orifice is flat which is giving this action. It is flattening it and flattening it to show that there is a plane contact between the two planes. So they have tried with different extrusion widths. तो extrusion width भी अलग-अलग जा सकती है. हमने तो height पे कर दिया 0.8 होना चाहिए. Width कितना हो सकता है? So they have tried with different and the good properties are obtained around 120. So it is suggested that your width should be 120 at least. जैसे 20% wide increase किया 20% behind increase करेंगे और max हो जाए 200 उसके beyond उससे beyond फिर properties डालें. So layer height minimum 20% and maximum 80% of your work. Similarly, line width minimum 75% and maximum 200. Minimum means possibility to print, but it will give you lesser strength of properties. So good combination is around 1. So this is achieved by the ratio of extrusion flow rate and your printing speed. So you have to balance the two. At which rate your extrusion flow rate is decided by the two rollers which are feeding your filament into the channel, heating channel. So they are creating the pressure to define the extrusion flow rate. And another thing is the printing speed of the work hand. Next point about the support structure. Yes, we definitely require these support structures either intentionally, as I have given that one example. And another thing is where there is an overhand kind of geometry in your component, you have to provide it a support. So different material support different orientation. If I talk about PLA, as PLA is very print friendly material, so it can print at 65 degree orientation without any support, maximum. While APS, which is temperature sensitive, it can print only 45 to max 50 degree. This orientation is, the books define this orientation in two terms, either with the vertical, angle with the vertical, or angle with the horizontal. So, in all kind of polymers, it is observed that 45-degree angle is acceptable for all kind of materials. The 45-degree orientation can be printed without giving any support structure. So that's it. You can say a rule, general motion is made. And yes, support structure is actually waste material which have to be removed after printing your part. So we have two issues that this is a kind of necessary evil. We have to provide it. At the same time, we have to minimize it because we have to discard it. It's of no use. You just can recycle it. Another thing, it has a detrimental effect on the quality, print quality of the part. Because जब आप support structure को remove करेंगे, तो surface पे scratches आएंगे वो आपने जब इसको break करते हैं या melt करते हैं, कुछ chemical में melt होते हैं, दो तरह के आते हैं, तो वो तो कोई pressure नहीं देंगे, but process will be costly and time taking. It takes around 8 to 20 hours to get dissolve the whole support structure. और उसके लिए क्या होगा? We have to make our FDM machine more sophisticated. We need dual extruder. एक से support structure अलग आएगा, एक से print material अलग आएगा. क्योंकि अगर सेम ही मटेरियल जैसे प्रिंट करते हैं उसमें सपोर्ट भी सेम मटेरियल का है और योर प्रिंट मटेरियल इज आल्सो. So in those cases we just have to break it. We don't have any option. क्योंकि हम मैच तो कर ही नहीं पाएंगे, दोनों का मटेरियल सेम है. तो केमिकली डिसॉल्विंग तभी होगी जब वो केमिकल डिसॉल्विंग मटेरियल आपने सपोर्ट के लिए सेलेक्ट किया और सेलेक्ट किया है तो उसके लिए अलग नॉलेज चाहिए, पहली सोफिस्टिकेशन. दूसरी क्या है, उसकी पाथ प्लानिंग अलग बनेगी, उसकी जी कोड एफ कोड वो एक्सट्रूडर अलग देगा और प्रिंट मटेरियल के जी कोड एफ कोड अलग होगा. तो प्रोसेसर भी आपका डबल लगेगा, मशीन की कॉस्ट बढ़ेगी. अभी जो जनरली यूज करते हैं वो सिंगल एक्सट्रूडर होता है. अगर डबल एक्सट्रूडर है भी तो आप देखना वो सेम पार्ट को कॉपी करते हैं, बस प्रिंट कर देता है, सेम ज्योमेट्री दो पीस बनाते हैं, पर सपोर्ट और एक्सट्रूडर को अलग अलग मटेरियल नहीं देता. तो ये इशू होता है. सो ये हमारा सपोर्ट स्ट्रक्चर का जैसे जनरली 45 डिग्री का ओवरहैंग कैन बियर विदाउट एनी सपोर्ट. तो हमें सपोर्ट की जरूरत नहीं है. Like this example you can see they are producing such holes. So vertical hole में कोई जरूरत नहीं है, but while the axis of hole is horizontal, then definitely you need a support structure like this. Okay. One criteria was about the overhang angle, है ना, 245 का हमने fix किया. Another criteria is about the overhang length. जैसे टी शेप आप बना रहे हो, ब्रिज बना रहे हो, तो कितने एंगल तक वो एडजस्ट कर सकते हैं, कब मेरे को सपोर्ट चाहिए या इसमें पूरे भी चाहिए. जैसे आप इस एग्जांपल में देख सकते हैं, यहाँ पे कोई सपोर्ट नहीं है, यहाँ पे कोई सपोर्ट, यहाँ पर कोई सपोर्ट नहीं होगा बिकॉज एंगल है चेंज हो गया. और जो ये मैं एंगल आपको बता रहा था 65 55, दिस इज फ्रॉम वर्टिकल. इनमें वर्टिकल से एंगल आप देख सकते हैं 45 से कम है, इसने आराम से फिट कर दिया. जैसे वो यहाँ पे आया तो आप 45 या 65 से ज़्यादा हो गया तो आपको सपोर्ट देना पड़ेगा. फिर जो लेंथ की बात कर रहे हैं, जिसमें टी सेक्शन प्रोड्यूस करता हूँ और प्रिंट करता हूँ, तो आप देख सकते हैं ये ऐसे शाइनिंग होगा क्योंकि हवा में लगेगा एक पार्ट ऐसे करेंगे प्रिंट, तो वो won't have any support, so this structure will be like this. So exact value is determined through experiments, but literature says that 10 mm overhang can be supported without any support. 10 mm तक जैसे कि सपोर्ट तो है, इससे 10 mm तक overhang without any support can be. Little bit sagging is there on the bottom. ये तो डिपेंडिंग अपॉन योर रिक्वायरमेंट, और ये तो एक तरह से एक्सपेरिमेंट करके देखना ऐसे आपका पार्ट डिजाइन करें. So support आपका पार्ट is in two ways. One shape is accordion and another is tree shape. Accordion means जैसे हम रूफ वगैरह लगाते हैं तो आपने देखा होगा नीचे से सपोर्ट दिया जाता है, जितने पिलर सपोर्ट के होंगे बॉटम से जाएंगे फ्लोर से, so that kind is accordion. और जो ट्री लाइक है नीचे एक होगा और ऊपर जाके ब्रांचेस बनते हैं लाइक there is a one pillar from the bottom and on the top you have 5 points for the support. So this is tree shape. तो ट्री शेप में क्या होता है, नीचे कम वॉल्यूम एंगेज होता है और सपोर्ट पॉइंट ज्यादा जनरेट होता है. So वो जो डायनामिक का मैं आपको बता रहा था, सपोर्ट without any support overhang, जैसे कि से बनाया, you can see this case. So diagram we call it as YST test. एक ब्रीजिंग पॉइंट अभी लगेगा. इसमें आएगा, मैं आपको ये बात कर चुके। हाँ, ये क्राइटेरिया डिसाइड कैसे किया कि 45 का है। 45 पे प्रिंट करने का मतलब है कि आप 50% मटेरियल ओवरलैप है और 50% हैंड क्लियर, एक क्लियर आप प्रिंट कर चुके हो। दूसरी उसके ऊपर प्रिंट कर रहे हो तो एटलीस्ट 50% सपोर्ट करने के लिए रहे। जैसे ही आपने 60% ओवरहैंड कर दिया और सपोर्ट के लिए 40% छोड़ दिया तो वेट सेंटर ऑफ ग्रेविटी इधर हो गया, so at max it can be balanced at 45 because weight will be distributed 50-50. 50 the support or 50 overhand, it can manage. But जैसे उससे ज़्यादा होगा तो नहीं। ये तो from that point this 45 degree angle is decided. So ये कुछ है। इधर अवॉइड करिए कि आप डिजाइन में कुछ ऐसे चेंज कर दीजिए ग्रेजुअली एंगल को सेट कर दें। हाँ, इसकी मैं बात कर रहा था, दिस इज कॉल्ड एबीसी और वाईएसटी टेस्ट। जब भी किसी मटेरियल का मान लो आप जिस मैन्युफैक्चरर से वी आर परचेजिंग पीएलए एबीएस और एनी पॉलीमर कंपोजिट, so it is he or she, that manufacturer is giving us the whole standard sheet that this material has this properties and this printing angle, the bed temperature, modular temperature, all process settings are suggested by the manufacturer. But now the case is you have designed your own polymer composition and you do not know that how much support angle will be, overhang length, overhang angle you can be able. So for that purposes, for the newer material, this testing is recommended called the YST test. So in the Y shape, you can see this is the overhang angle. So you can check with different Y hands. Similar, this H shape is giving us a case of breathing. Cantilever की तरह simply supported beam की तरह होगा. So this part, so ये breathing कितना allow करता है between two supports. So 20 mm support length is suggested without any support.